Good afternoon. It's splendid to have so many people here around. I am happy because I am starting to believe that Facebook is something existent, really. I didn't have trust at all. And it's, of course, a great pleasure and honor for us to have this legendary physicist here. For those who already visited this lecture at our faculty, by the way, I am from theoretical physics, from faculty, because there are many people whom I don't know, they probably also don't know me. But you will suffer from similar introduction, but I think because there are many people who were not at this talk, so I will use the same slides in a while. But I wanted first to say that it's actually quite nice moment for Professor Thorne, because it was here in this building, and I think in this room, where he first time met people who then became very closely related to him from completely different camp, also with similar ideas about politics, I think, and that was the group of Jakov Borisovich Zeldovich. Because in 1967, there was a big IAU symposium here, and Kip met Zeldovich, Novikov, and other people. I think also Martin Rees probably. So all these people gathered here, and we didn't realize in those days still in what big fields, relativistic astrophysics, primarily thanks to Kip, and also, of course, to group in Moscow will form and will arise. So if you would be so kind, Kip, he's projecting my pictures. So I'm sorry to repeat the same joke, but there are many here, and it's not a joke really. I'm saying this is the grandfather of Professor Thorne. And it has some deeper meanings that it's not only a joke. First of all, Kip spent most of his professional life, scientific life, at California Institute of Technology at Caltech. And this is on the soil of Caltech where Einstein is fighting with gravity. But the other reason is deeper, namely that, as you know, Einstein spent his last years, actually decades, not just years, in Princeton. And the follower of Einstein in Princeton was Professor Wheeler. Since I assume there are many people who might not know about John Wheeler, so he was one of the biggest American physicists who started with nuclear physics, who, however, in the 50s started to be deeply interested in developing theory of gravity and looking at the new things which were slowly discovering, like pulsars, quasars, etc. And he created the most influential group, I would say, in the United States in relativistic astrophysics, and they were always in competition with the group of Zeldovich in Moscow. Wheeler was also the mentor of Richard Feynman, and Professor Thorne is actually Feynman Professor of Theoretical Physics, emeritus. And so he is really forward. He was the first Feynman professor because Feynman died in '88, and Kip Thorne became professor in '91, I think, Feynman professor. And he was one of the youngest professors at Caltech when he was already 30, when he only 30 years old. I have another two, if you would be so kind, transparencies. This is how I was happy and lucky that I could experience Professor Thorne at the beginning of the 70s. Unfortunately, only for a couple of months. It was not allowed, but by our nice party, to be there longer. But in any case, it was very influential and enormously impressive. And Kip always spoke with people and was admired by young people. So this is after the lecture when the sun stops to shine. It was apparently about gravitational collapse and formation of black holes. And the last slide is first time when I am using it here. This is very typical for Kip Thorne, namely that he made a lot of bets with his students, but also with experts in the field. So as you see here is whereas Kip Thorne, professor, believes so strongly that the universe is logically constructed and hence can be understood, and whereas William Burke, student, entertains serious doubts concerning this universe, that herewith a vague or wager is accepted, whereby Kip Thorne gives odds $25 to $1 that the universe is so constructed whereby William Burke accepts the challenge to find a contrary instance, and to wit, to give the proof is that the nonlinear post-Newtonian gravitational stresses significantly affect the radiation in the lowest order for free-fall motions, and thereby causing a significant deviation from standard weak field theories that go on, say, on geodesics, it will be free motion. So you should first notice that Kip would give $25 if he loses, but student would give only $1 if the student loses. And Kip's word line then is accompanied by a number of various bets, although at the moment I think you don't have any bet now.
I have one that continues with John Preskill.
About
information lost down black holes.
Okay. Oh, I see. Okay. And so there was with Steve Hawking bets and with other people, and it always was nicely formulated. Well, in any case, so Kip is also very well known by these big books which he wrote, and you probably know all Meissner, Thorne, and Wheeler, which is very influential, probably the most influential book on general relativity and gravitation. But very recently, and this is really admirable, he wrote, admirable because he simultaneously did film, as I will mention just briefly, and then I will stop. And that is that they wrote with Blanford, very well-known astrophysicist, book which is called Modern Classical Physics, and which again, published in Princeton University Press, which again has about 1,500 pages. So I recommend this as a splendid textbook for plasma and everything, not so much about GR, although there are also mentioning about GR. But of course, what is probably to you known, not unfortunately to me, because I didn't see Interstellar, so Kip was the main scientific advisor of the Christopher Nolan film Interstellar. Probably many of you saw it. How many did you see Interstellar? Good. I should make a picture. It's quite a lot. So I'm ashamed. I just, for illustration, what is Kip's attitude to these things, will read what he wished. What should be or could be in film. Nothing in the film will violate firmly established laws on physics or our firmly established knowledge of the universe. Speculations, often wild, about ill-understood physical laws and the universe will spring from real science, from ideas that at least some respectable scientists regard as possible. Before finishing and saying the last words about Kip, I should thank to Karel Janeček, who supported his visit. It's a visit really of Learning Society of Czech Republic. Also our dean and faculty gave nice welcome, but it was Learning Society and Karel Janeček together who supported this visit. Oh, let me finish in the same way as I did in the previous two lectures which Kip already gave, namely quoting Richard Isaacson, who was governing money within National Science Foundation for research in gravitational physics, and in particular for LIGO and for gravitational waves. And so he said somewhere that Kip Thorne is actually our national treasure. And I'm saying that it is certainly international and worldwide treasure, but at the moment, he's treasure of our republic, or as I said, of Kingdom of Bohemia. Please, Kip.
Thank you, Yeshi, for that overly generous introduction. I'm going to be talking about the warped side of the universe. And by this, I mean objects and phenomena that are not made from matter like you and I, but instead are made from warped or curved or distorted space and time. And the examples of the warped side of the universe that I will focus on in this lecture, and these are not the only examples, but they're the ones I will focus on, are black holes, gravitational waves, the Big Bang singularity in which the universe was born, wormholes, and time travel. How could I talk about this without saying something about time travel? So, time travel. And let me begin then with black holes. And let me also begin by saying that, as I will conclude the lecture, when I began working in this field as a graduate student under John Wheeler in 1962, which is a few years ago, the idea of the warped side of the universe was there in the sense that there were speculations about some of these phenomena, that some of these phenomena might arise from Einstein's general theory of relativity, but there was no firm understanding of any of these phenomena. And what I will describe today is how things have changed in the years since 1962. I guess that's about something like 55 years, and where we stand today in our knowledge of these phenomena. Beginning with black holes, it was a classic analysis in 1939 by J. Robert Oppenheimer and his student Hartland Snyder, in which, triggered by earlier work by others, which said that if you had a very massive star, then when it died, it probably would not be able to continue to support itself against the pull of its own gravity after it had exhausted its nuclear fuel, and so it would begin to shrink and it would collapse upon itself. And Oppenheimer and Snyder then analyzed, using Einstein's general theory of relativity equations, what would happen in that collapse in the idealized situation where the star was homogeneous. It was the same everywhere in density, and it had negligible pressure. But the earlier work by Oppenheimer and others had said that the pressure, even if you had huge pressure, it probably would not be able to prevent this collapse. And so what he found was, as the star collapsed and imploded on itself, became smaller and smaller, ultimately a point was reached at which, at the surface of the star, time slowed to a halt. Time ceased to flow at the surface of the star compared to the rate of flow of time back here on Earth. And gravity became so strong that nothing could get out. Theoretical physicists around the world fought against this prediction for several decades. John Wheeler, my thesis advisor, was among those who fought against it most vigorously until further analysis from other points of view made it crystal clear that this prediction was firm. And it was after that, a few years after that, that John Wheeler coined the name black hole for this object that's left behind. Black hole is an example of an object on the warped side of the universe. It's made from warped space-time. For example, if I have a black hole and I try to measure the diameter across it, of course I would have to go inside and measure it, and I couldn't get out and publish my result. But if I go inside, I could attempt to measure it and then compare with the circumference. The diameter, I would find, is much larger than the circumference. And you would say, how could that possibly be? And let me describe this by an analogy. Suppose I take a child's trampoline, that is a sheet of rubber that is standing up on high sticks or high poles, and I put a rock down at the center of this. And so it bends the rubber down in that kind of a shape. And then let's suppose that I'm an ant, but I'm a blind ant, and so I can't see what's going on here. But I have studied physics here at the Charles University, and so I know that it's a wise thing to do to measure the circumference and then try measuring the diameter. And I walk and I walk and I walk, and it's a very large distance to get to the other side. And so the diameter is far larger than the circumference. And having a degree in physics from the Charles University, I can quickly realize that the reason is because the universe in which I live is warped. It's distorted in just the manner that we see here. And this same diagram, in fact, with no changes except labels, holds for a black hole. If I take a black hole and I take a two-dimensional surface through the equator of the black hole, the geometry of that surface is not flat like the surface of this table. Rather, it is bent in precisely this way, but its bent is seen from a higher dimensional space, which physicists sometimes call the bulk. In the movie Interstellar, it's called the fifth dimension because we have 3 space dimensions, and time is the 4th dimension. This is the 5th dimension. But you're looking in from a higher dimension, from the bulk, and you see just this diagram, which depicts then the warping of space in the equatorial surface of the black hole as seen from a higher dimension. Diameter is huge compared to the circumference. Of course, that's not the main thing that we know about black holes. We know that if I fall in, I cannot send signals out. So here I am falling in. I'm a 2-dimensional Kip on the surface, on this 2-dimensional surface, because I have removed 1 space dimension from the diagram. And so I have to draw myself as 2-dimensional. I have a microwave transmitter. I'm sending signals out with the microwave transmitter, but once I fall through the surface of the black hole, which we call the horizon, those microwave signals are pulled downward toward the center of the black hole along with me. At the center, instead of a rock, there is what we call a singularity. It's a place where gravity is so intensely strong that Einstein's laws of general relativity fail and must be replaced by a new set of physical laws called the laws of quantum gravity. I won't talk very much about such singularities here today. Singularities are examples of another kind of phenomenon on the warp side of the universe beyond the ones that I'm discussing. But it's not just space that is warped in a black hole, it's also time. So that if I go down closer and closer to the horizon of the black hole, hovering there, not falling in, I will find that time as measured by my clocks or by physical phenomena in my body, biological time, is slowed down compared to time back on Earth. And as I reach the horizon and I hover there, I stay there at the horizon, time is seen by me. It feels normal to me, but when compared to what's happening on Earth, my clocks, my body clock, all clocks that I carry have stopped ticking. Time has stopped to flow compared to the rate of flow of time up above the Earth. And inside a black hole, what can be slower than stopped time? Well, time actually flows in a direction you would have thought was a space direction. It flows downward toward the singularity, and that is another reason you can never get out of a black hole when you have fallen into one. Because to get out of the black hole, you would have to move backward against the local flow of time. And that is undoubtedly impossible. When I talk about time travel at the end of the lecture, I'll talk about going backward in time by traveling out through the universe and coming back before you started. That conceivably may be possible, but you cannot go backward against the local flow of time. And so, in the sense the local flow of time is toward the singularity, you cannot get back out of the black hole. That black hole, the exterior of the universe, the entire exterior of the universe is in your past. In addition, black holes like the Earth turn on their axes. They spin, and that spinning creates a whirling motion of space, which we call the dragging of inertial frames, but very much like the whirl of air in a tornado. It's fast near the horizon, as indicated by this arrow, and slower farther away from the horizon. This is a precise depiction, then, of that warping of space and time outside the horizon. The horizon here looks like a circle, but when I restore, I bring back the 3rd space dimension, then it becomes a sphere. And the distant regions of the universe are out here. This surface becomes flat far away, but near the horizon, the surface bends down in just the way that we saw in my other heuristic drawings. But this is the precise depiction of that warping of space. The colors are the precise depiction of the slowing of time. Where it is yellow, time is flowing at 10% of the rate that it is back here on Earth. And at the horizon, time is not flowing at all. It is slowed to a halt. And if the so this was for a non-spinning black hole, but I wanted to make the further remark or to ask the question, what is it that warps, that distorts the black hole's space and time? The answer is quite peculiar. The only thing that can warp space and time is mass or energy. Energy and mass are equivalent according to Einstein. So if I talk about energy, it's the same thing as talking about mass. The mass or the energy that warps the space-time of a black hole is the energy contained in the warping itself. In other words, the black hole is held together by what we call, as physicists or mathematicians, a nonlinear self-interaction. It's the energy in its warping produces the warping. And that is really quite peculiar, but similar kinds of things are seen elsewhere in physics, this kind of nonlinear self-interaction that holds an object together. Another phrase for a black hole is a gravitational soliton, for those who know what solitons are in other areas of mathematics or physics. If the black hole is spinning fast, then the throat going down to the horizon is much longer, so things could get trapped down here more easily, and I talked about that at the end of my technical lecture yesterday. And this is a precise depiction of the angular velocity of the whirling of space, fast near the horizon, slow farther away. Let me now restore that third dimension to space, but abandon trying to describe the warping of space. And so I have here then the North Pole region of a large black hole, and I have put my wife, Carolee Winstein, who's here, hanging above the horizon. And as she looks down from her head to her feet, because the black hole, because the dragging of space into whirling motion is faster near the horizon than it is farther away, she sees her feet turning faster than her head. So as seen by her head, her feet are whirling around in a counterclockwise way. And as seen by her feet, her head is turning around in a counterclockwise way. And so this is just like if you take a wet towel and you try to remove the water from it, you twist the towel. And you think about it, if your right hand sees your left hand turning counterclockwise, then your left hand will see your right hand turning counterclockwise. So there's a counterclockwise twist to the towel and a counterclockwise twist of space at the horizon. And we call this a vortex, borrowing a term from the theory of fluids and from familiar ideas of a vortex in a bathtub. But it's a vortex of twisting space. And it turns out that at the South Pole, there's a clockwise vortex of twisting space. And so you have, sticking out of a spinning black hole, you have two vortices of twisting space, one counterclockwise, the other clockwise. And these are just as real as my hands and my arms sticking out of my body. But those vortices are not made of matter like my hands and arms are. They're made of warped space-time, twisting space-time. Well, twisting space as time passes. And I'm going to return to these vortices a little bit late in my lecture. Let me talk for a moment about black holes in our universe. We, over these many decades since I began to study this subject in 1962, we have learned through astronomical observations that there are approximately 10 million black holes in our Milky Way galaxy, and roughly a billion black holes in the universe. So that's a lot of black holes. Of course, there are a lot more stars than that, many more stars than there are black holes, but still, this is a lot of black holes. And black holes have a wide range of sizes. They range in mass from about 3 times the mass of the sun up to about, the observed black holes, nearly 20 billion times the mass of the sun. And they have diameters that range from about 10 kilometers to about 100 billion kilometers. The diameter is proportional to the mass of the black hole. So there's a huge range of sizes and masses for black holes in our universe. And we have extensive observational evidence for them. They are seen in many different ways, or their influences are seen in many different ways by astronomers. What would a black hole look like to your eyes if you were up close to the black hole? Well, we can figure this out by drawing the paths of light rays going from a star here through the warped space of a black hole to a camera there. And one route is along this light ray, but there's also another light ray along which light from that star can travel. It goes around the other side of a black hole. These light rays are bent by the warped space and the gravity and the warping of time in the vicinity of the black hole. They all contribute to this. And there's also a light ray that goes down and around very close to the horizon back up to the camera. And there are a lot more light rays that go down and around the black hole many more times in one direction or in the other before coming to the camera. But it should not surprise you to know that there's this shadow here where no light rays can come from that star to the camera. And so in that region, you just, there's no possibility to see that star or any other star. And so here for the three light rays that I have shown you is an image that from computer simulations that shows one image of the star from that light ray, another image from this light ray, and one very near the shadow of the horizon from this light ray that goes down very close to the horizon and back up. Now, in reality, of course, there are many, many stars in the universe, and so again, this is from a simulation. This happens to be a simulation solving the propagation of light around a black hole as seen by a camera. But this simulation was interestingly done by the team that built the visual effects for the movie Interstellar. That is, the things you see about astrophysics in that movie are all very realistic. They're based on solving Einstein's equation for the propagation of light, for example, around black holes. But I just want to show you, this is just a field of stars, a uniform distribution of stars, basically. But you see patterns in here caused by this gravitational lensing, the bending of light rays, and the fact that there are many different light rays along which the light can travel. And it's quite remarkable. This is as the camera moves around the black hole. This pattern here is called an Einstein ring, but there are a lot more Einstein rings down here, down there, down there, down there. A whole series of Einstein rings that are associated with what we call caustics of the past light comb of the camera. It's for people who know the mathematics or the physics of this. And it's quite interesting to see these patterns caused by gravitational lensing. But most black holes are actually surrounded by disks of hot swirling gas, and they may not even just be disks, they may just be big patterns, swirling patterns of gas around the black hole. This is a particular simulation by Jordi Davelaar at Radboud University in the Netherlands. And you see the disk going around, you see a very thick configuration of gas swirling around the black hole. And so you don't see the gravitational lensing of the stars as an astronomer sitting back here on Earth. Where do these disks come from? Well, basically, at least in many cases, they're caused by a black hole tearing a star apart. When the star gets too close to the black hole, the side of the star that's close to the closest to the hole is pulled by the hole's gravity more strongly than the far side. And the entire star is pulled apart in that way. And I'm going to show you a computer simulation then by James Guillaucon and Suvi Jazari, two postdocs who did this simulation, not my postdocs, but this is the nicest simulation I know. Up in here is the black hole, there is the star that is going to go down, go around the black hole and get torn apart. So I've put this box here, or they have put the box here just to show you where the star is and where the black hole is. Now you watch what happens. Okay, it went around the black hole, and then some more of it went around, and the black hole is obviously down here, and some of this gas gets captured by the gravity of the black hole, forming this pattern of, this disk-like pattern of hot gas swirling around, and the rest goes flying off into interstellar space. So that's where these disks come from. And so one of the great discoveries of the last several years, one of the most important discoveries yet ever observationally about black holes, was the observation of and the actual imaging of a thick disk of whirling gas around a black hole in the center of the galaxy M87 by what is called the Event Horizon Telescope. And this image that I'll show you, that many of you have seen in the newspapers or on the web, this image then was produced by the Event Horizon Telescope, it's called, which is actually a number of radio telescopes at various locations around the Earth. And the data from these radio telescopes are all brought together and combined coherently, is the technical word, coherently, to make an image that has the resolution that we would have if you had a radio telescope that has the size of the Earth. So it's really very impressive. The shorter the wavelength radio waves you use, the more accurate the image is. And the larger the spacing of the telescopes, the more accurate the image. So we've already got the telescopes that are the largest separations you can do without going into space. There is one radio telescope that can be used for this that is in space, a Russian radio telescope that could be a contributor in the future to this kind of thing. But the current technology allows only using radio waves with wavelengths of 1.3 millimeters and not shorter. And using 1.3 millimeter wavelengths and a combination of telescopes that span the Earth, 400 scientists and engineers at 100 institutions in a collaboration led by Shepard Doleman at the Harvard-Smithsonian Astrophysical Observatory had success last month in imaging the black hole and its disk in the M87 galaxy, and that's the image that they made. And you see the image is very bright on this side and quite dim on that side for a very simple reason. The black hole is spinning on its axis. The disk is actually dragged into motion along with the spin of the black hole. When the gas is close to the black hole, it has no choice except to go with the flow of the spin of space, just like straws or cows or houses caught in a tornado whirling around. And so the gas is moving toward us on this side, so there's a blue shift and it's much brighter, and away from us on that side, so there's a red shift, it's much dimmer. And just looking at this, you can infer basically that the black hole is spinning around an axis that is something like that, and the gas is whirling around like there, from the brightening on one side, the dimming on the other. And from the size of the image of the horizon, the shadow of the black hole's horizon, and knowing the distance away to this black hole in the M87 galaxy, they could infer that this black hole weighs 6 billion times what the sun weighs, which is one of the biggest black holes, but not the biggest black hole that is known. We have a massive black hole, but 1,000 times less massive than M87 at the center of our own galaxy. This black hole has a mass of 4 million solar masses. We don't see it by imaging an accretion disk. We see it by the motions of stars around the black hole. So this is from a visualization of the orbits of these stars. The orbits were measured by Andrea Ghez and her collaborators at the University of California at Los Angeles. And you see these stars going in and around, and from the where things are whirling around tightly, it's obvious the black hole is down in here. And the Event Horizon Telescope team expects to image this black hole as well within the next year or two. They're working hard on it, and I'm looking forward to seeing the images. And as the wavelength of the radio waves that are used gets smaller and smaller as technology improves, then we expect to see higher and higher resolutions. And we also will be seeing how the gas flow changes and how turbulent or non-turbulent the gas flow is around these black hole horizons. So really very interesting. Well, that's all I want to say about black holes. Let me turn my attention to gravitational waves as my second example. I've already talked about gravitational waves in my first lecture. I will duplicate a small piece of this, but I want to mostly discuss things I didn't describe in my first lecture. My first lecture was about creating gravitational wave astronomy, the process by which we came to be able to observe gravitational waves. But I'll begin, as I did in the first lecture, with Einstein's predictions in 1916 using his equations of general relativity theory, his prediction of gravitational waves. And what he said is, in his calculation, if you take a rectangular grid of particles, and they're just laid out in interplanetary space where there's negligible gravity from anything else, and these particles are at rest with respect to each other, they will remain at rest with respect to each other. And a gravitational wave comes through, passing through this grid of particles perpendicularly. So if the particles are in the plane of the screen, it's passing through perpendicularly into the screen. And what the gravitational wave does is it pushes the particles apart along one direction and squeezes them together along the other direction. Then pulls them apart in this direction and squeezes them together in that direction. You can think of this as be due to a stretching and squeezing of space. And so here is the pattern as I described it, a stretching and squeezing of space by the gravitational wave. Now, there are only two types of waves, according to the laws of physics as we understand them. Two types of waves that can be created in the distant universe, travel across the universe to Earth, bringing us information about what's far away. They are electromagnetic waves. These are oscillations of the electric and magnetic fields. They comprise light, radio waves, X-rays, gamma rays. And their gravitation and electromagnetic astronomy with instruments was created 400 years ago by Galileo when he built a small optical telescope, pointed at Jupiter, discovered the four largest moons of Jupiter. And the other type of waves is gravitational waves. And the goal of our project, in which I was deeply involved, called the LIGO project, was to do for gravitational waves what Galileo did for electromagnetic waves, to build gravitational wave detectors and look at the sky and discover gravitational waves and begin then to use these detectors to create gravitational astronomy. And we did succeed, though it was about a 50-year effort for me and the others who were involved in the beginning of it. Gravitational waves are, and that's the story I told in my first lecture. Gravitational waves are made from the same thing as black holes. They're made from warped space-time. So they're the ideal kind of wave to study the warped side of the universe, the ideal tool for exploring the warped side. Ray Weiss was the person who invented the kind of gravitational wave detector that we use in our LIGO project, that we used in order to do what Galileo did. And Ray described this in a technical paper he wrote in 1972. He said, let's hang, this is not quite the version that he described, this is a version that was slightly improved by somebody else who was involved in starting this project, Ronald Drever. But the basic ideas under this are, that were largely due to Weiss. And what you do is you hang 4 mirrors from overhead supports, hang them by wires, or in our current incarnation by fused silica, that is quartz fibers. These mirrors in our current detectors weigh 40 kilograms, so they're very heavy. When the gravitational wave comes along, it pushes these mirrors apart, pushes those together, and then later it pushes these apart, pushes those together. And we use laser beams to monitor that changing difference in what we call the length of this arm and the length of that arm. This is a technique called laser interferometry, and I won't go into the details. All you need to know is we use laser beams to monitor the changing, the stretching and squeezing of space along those two directions. Because we use a technique called laser interferometry, this is called a gravitational wave interferometer. Well, that was 43 years of work from that point onward, though Ray had already been working on this for more than 7 years, and I'd already been working on this for more than 7 years. So it was a little more than 50 years for each of us. A very intense work from that point onward by a team that grew to more than 1,000 scientists and engineers in the manner I described in my first lecture, and led ultimately by 2015 to 2 gravitational wave interferometers, one in Livingston, Louisiana, and the other one in Hanford, Washington, in North America. And this is called the Laser Interferometer Gravitational Wave Observatory, or LIGO. And so I've jumped over a long story that I told 2 days ago in my lecture, but I will tell you what happened once again for those who heard it, because it is such a beautiful, beautiful ending to 43 years of effort by what amounted to over 1,000 scientists and engineers. So 1.3 billion years ago, in a galaxy far, far away, as Carl Sagan used to like to say, there were two black holes, and you see the shadows of these two black holes, one shadow there and one there, through gravitational lensing by light from distant stars. These black holes orbit around and around each other, and as they orbited around each other, they emitted gravitational waves which carried away orbital energy, causing the black holes to spiral gradually together, getting closer and closer together, and the waves getting stronger and stronger, until ultimately the black holes came crashing together in a gigantic cataclysm, producing an enormous burst of gravitational waves, which carried off as much energy as you would get by annihilating 3 suns and turning all of the mass of those 3 suns into gravitational wave energy. And that energy came off so fast, in about 1/10 of a second, that the power output, the luminosity, was 50 times higher than the luminosity of all the stars in the universe put together, for a brief period of about 1/10 of a second. That burst of gravitational waves traveled outward from the galaxy in which the black holes lived into intergalactic space, traveled for 1.3 billion years across the great reaches of intergalactic space, until back 50,000 years ago, when our ancestors were sharing the Earth with the Neanderthals. That burst of gravitational waves reached the outer edges of the Milky Way galaxy, and for 50,000 years it traveled onward until on 14 September 2015, it reached the Earth, touching down on Earth at the Antarctic Peninsula, traveled up through the Earth, and as remarked here, this was 3 days before we were beginning to, planning to have our first gravitational wave search with advanced LIGO gravitational wave detectors. And so it came in 3 days early, but fortunately our instruments were operating properly. And the director of the LIGO project, David Wright, he declared that our search had begun 3 days early, triggered by this burst of gravitational waves. The waves traveled upward through the Earth, emerged at the interferometer in Livingston, Louisiana, and then 7 milliseconds later at Hanford, Washington. The data from the stretching and squeezing of the arms of these interferometers went into a computer and was analyzed by a computer program that had been written and perfected by the team. That computer program made an internal web page that had the details of the signal on it. Then we, as members of the team, woke up the next morning, at least in America. It was, I guess, already the next morning in Europe. We woke up the next morning to the announcement from this computer that maybe we have seen a burst of gravitational waves. It took 5 months for the team to be absolutely sure, this 1,000-person team. And when we ultimately then were absolutely sure and had cleaned up the signal in terms of stretching plotted up and squeezing plotted down as a function of time is the gray area, and the prediction from a computer simulation is the red trace here. And by comparing a computer simulation of colliding black holes with the observations, we inferred indeed that the initial black hole weighed 29 times what the sun weighs and 36 times what the sun weighs. The final black hole was 62 times what the sun weighs. 3 solar masses went off in gravitational wave energy, and the distance to the source was 1.3 billion light years. And so the computer simulations working together with the observations were crucial to understand that we really had seen now colliding black holes and what the properties of the black holes were. We announced the result to the world on February 11, 2016. It made headlines around the world. By now, LIGO has seen 16 black hole collisions, 2 new collisions of neutron stars, which I won't talk about in detail. Our third search, we've gone through 2 searches, gradually improving these detectors. Our third search began on April 1 with improved detectors. There's a smartphone app that you can just get for your smartphone called Gravitational Wave events, or GW events, onto which go the observational data as analyzed by the computer, and then corresponding searches by electromagnetic astronomers for associated electromagnetic waves with each event that comes in. And those data go onto this smartphone app within minutes of when the signal arrives, because we're providing it to the world of astronomers so they can go search for any other kind of emission from this event. This is what I saw in this morning. It's changed since my lecture 2 days ago. There has been one more black hole collision seen. What I want to highlight today, this is just what I noticed this morning is when I was preparing the lecture, is that in fact, in the past 5 days, there have been 3 black hole collisions. That's quite a change from when we were seeing them about once a month early on. 3 black hole collisions in the past 5 days. 3 weeks ago, there was a neutron star collision. And you can follow this day by day, and I do look at it every day just to see what has happened. The most recent one came in today. It was not there when I woke up this morning. It was there when I prepared this slide. It came in between the time when I woke up and when I prepared this slide later in the morning this morning on the 17th of May 2019. So as I said, LIGO's now seen 16 black hole collisions, 2 neutron star collisions. By the 2030s, we will likely be seeing waves 20 times weaker than we're now seeing. We will likely be seeing every black hole collision in the universe where the black holes are less heavy than a few hundred times the mass of the sun, and a wide variety of other warped side of the universe phenomena. So this is really exciting. We are beginning to explore the warped side of the universe. And by the 2030s, we will be seeing gravitational waves in 4 different gravitational wave frequency bands, or wavelength ranges. With LIGO and its international partners, gravitational waves that oscillate with periods of milliseconds. With LISA, a laser interferometer space antenna built by the European Space Agency, 3 spacecraft tracking each other with laser beams, gravitational waves with periods of minutes to hours, and LISA will see black holes colliding with that weigh between 1,000 times the mass of the sun and 10 million times the mass of the sun. LISA will map the geometry of warped space-time around a big black hole with exquisite precision, and it may watch the birth of the electromagnetic force. I will return to these in a little bit of detail because these are good examples of exploring the warped side of the universe that are really quite exciting for the future. Then there's a technique called pulsar timing arrays that will see black holes that are heavier than LISA sees, between 10 million and 10 billion times the mass of the sun. And a technique I will say a little bit about in a few minutes called CMB polarization that will see black holes with periods of oscillation of hundreds of millions of years. And with this instrument, we expect to observe the Big Bang birth of the universe, the singularity in which our universe was born, and see the influence of the extremely rapid so-called inflationary expansion of the universe in the first tiny fraction of a second. And we expect to see that also later on in this century with something called Big Bang Observer, which is similar to LISA but much more complicated and far more accurate and far more sensitive. So we expect by the middle part of this century be studying the birth of the universe in 2 different wavelength bands, or period of oscillation bands, minutes, periods, and periods of hundreds of millions of years. That's really very exciting. So this gives you, again, some sense of aspects of the warped side of the universe that we're going after. Now, let me talk about LISA just for a moment. So LISA is 3 spacecraft that track each other with laser beams. The precise separation between the spacecraft is not firmly fixed. When this particular drawing was made, it was 2.5 million kilometers. It may be 5 million kilometers. It's likely to be launched around 2030 if we're lucky, maybe a few years later if we're not. As I said, it will study giant black holes with masses of millions of suns. And let me give you then one example of these kinds of studies. I have here a great big black hole, a very massive black hole, and a small black hole going around the big black hole. And let me show you what the orbit of that small black hole looks like if I remove the warping of space and I turn this into a 3-dimensional image. And so, well, let me show that and then I'll comment on it. So here is the small black hole going around the big black hole. The black holes are purple, and I'm afraid that with the glare of the light, you may not be able to see it very well. But I think you can see that the orbit is very complicated. By contrast with the orbits of the planets around the sun, which are nice ellipses, this orbit is basically winds around in complicated ways due to the dragging of space into motion by the big black hole, due to the warping of space and warping of time by the big black hole. The small black hole basically explores the whole region of space around the big black hole over a period of a year as it goes around the big black hole many tens of thousands of times. And an analysis by a student of mine in the 1990s, Fintan Ryan, showed that contained in the gravitational waves emitted by the small black hole as it explores the warped space-time of the big black hole, contained in those waves there is a full map of the entire warping of space and time and the whirling of space around the big black hole that's explored by the small black hole as it moves. And so from those waves, if the data can be analyzed and the signal extracted, and that's a very difficult problem that is currently being attacked by the LISA team, and they're far enough along, I think we're fairly confident they can pull it off. If they can extract that signal and analyze the data properly, they can build a map like this map, like the ones I've been showing, of the warping of space, the slowing of time, and the whirling motion of space around the big black hole, in the same way as NASA and ESA mapped the surfaces of Mars and of Venus. And so it's really quite exciting to be able to do this mapping. And what if the central body turns out to not be a black hole? For example, what if it's a singularity like the one that I told you is in the center of a black hole, but it's not hidden inside a black hole, a naked singularity just sitting there? Then what happens? Well, it turns out, at least in some cases of singularities, one due to Igor Novikov and his colleague Manko, the orbit of the small black hole near the big black hole is chaotic in the sense of mathematical chaos. And you will get a very, very different kind of map or attempted map from looking at the gravitational waves. And so we actually have the possibility to search for naked singularities by looking at gravitational waves from small objects going around very heavy objects in using LISA. We also will be exploring the dynamics of warped space-time in black hole collisions. We're doing that already with LIGO. We will do it with exquisitely high precision with LISA. This is a simulation that I have showed before 2 days ago. I want to show it once again. Here you have two black holes orbiting around each other. One of them produces this sort of funnel going down, and the other one that funnel going down, just like we saw for a single black hole. The color coding is the slowing of time near the black hole's horizon. And as the two black holes orbit each other, and I'm going to go into slow motion now, the warped space-time as they start to collide creates a huge splash in the shape of space, much like the splashing of water in a giant storm at sea. And that an oscillation of the shape of space and of the rate of flow of time, and the gravitational waves come off. So that's what the black hole collision looks like as seen from the outside our own universe, looking in from the bulk. But But that is what, to me, is one of the most exciting things to explore about the warp side of the universe. We call this geometrodynamics. It's the dynamics of the geometry or shape of warp space and warp time produced when two black holes collide. It's what I like to call a storm in the fabric of space and time, and we are now exploring the details of those storms. This actually captures only a small portion of the space-time storm that's created by the black hole collisions. There also are, for example, the influence of the behavior of these vortices that I told you stick out of a spinning black hole. I talked about this in some technical detail in a lecture yesterday. I'll talk about it much more quickly, giving just the basic idea today. For simplicity, let me take two black holes that collide head-on. I want to do the simplest case that I can. And I have a counterclockwise vortex that is sticking up. This blue vortex is sticking out of there. I've taken the horizon of the black hole and I have given it a color of blue where there's a counterclockwise vortex of twisting space sticking out of it, and red where there's a clockwise vortex of twisting space sticking out. And over here, these vortices are in the opposite direction. So you have this whirling space here going in the opposite direction down there, then they're reversed over here. So you have four vortices, two on each black hole, and we'll just watch what happens to the vortices by the color of these spots, which tell you what kind of vortex, clockwise or counterclockwise, is sticking out of the black hole. So you're seeing the horizon of the black hole, the horizons merge, there's an oscillation. It was originally blue up here, now it's red. Now it's blue, now it's red, now it's blue. What you began with was four then vortices sticking out of the black hole. They fought with each other, they exchanged vorticity. The guy that was clockwise switched around, became counterclockwise as they fought with each other, and ultimately they destroyed each other and all the vortices were gone. In this particular case of a head-on collision. So what happened then to the vortices? Well, I depict this here at a particular moment of time when you have a blue clockwise vortex sticking out, or I guess counterclockwise vortex sticking out here. That vortex is described by these lines which basically guide this twisting vortex. They're called vortex lines to do the guiding. That vortex goes out of the blue spot here and goes back into the blue spot on the backside. This vortex, this red one, goes out of the red spot here and back onto the red spot on the backside. And as this oscillation goes on, whenever this goes green, these vortices have been thrown off of the black hole. And what happens when they're thrown off the black hole? They form a ring of vortices that are embracing each other, that travel outward at the speed of light. So you have ring after ring after ring, but each ring getting weaker and weaker. And as these vortices travel outward in a form of tori, like smoke rings, their motion creates the stretching and squeezing phenomena of what we call tendices, from tendere, the Latin to stretch. And so there's a stretching along this part of the ring and a squeezing along that part of the ring, and this is a gravitational wave. Gravitational waves consist of not just a stretching and squeezing, like I told you at first, but also embracing that. There is a twisting of space at 45-degree angles. But we don't know how to build gravitational wave detectors of good sensitivity that work off of the twisting of space. We only know how to detect with good sensitivity the stretching and squeezing of space. This just gives you a sense of geometrodynamics, what goes on in the warp side of the universe with phenomena, these vortices of twisting space that are not made of a matter like you and me, but they are made from warped space-time. We also expect to observe the birth of the universe and the birth of fundamental forces that govern the universe with gravitational waves. When the universe was 1/trillionth of a second old, the electromagnetic force and the weak nuclear force, two of the four fundamental forces of nature, But earlier than that, they were combined together into a kind of force that we don't normally see here on Earth called the electroweak force. As the universe cooled in its expansion, had aged about a trillionth of a second, that force came apart and created the birth of the electromagnetic force that we know and love so well through what are called Maxwell's equations. And that birth of the new forces, the electromagnetic force, is thought possibly to have occurred inside bubbles like water droplets. This is like water condensing out of water vapor, water droplets condensing out of water vapor. But these droplets, inside of which there is such a thing as electricity and magnetism, outside electricity and magnetism don't exist. These are predicted then, if this is the way it happens, to expand at nearly the speed of light, collide, and produce strong bursts of gravitational waves in the collision of these bubbles. And these gravitational waves are predicted today, although they were created when the universe was a trillionth of a second old, they are predicted to be in LISA's frequency domain. And so we hope to watch the birth of the fundamental electromagnetic force through these stochastic gravitational waves that are created from the bubbles in which, collisions of the bubbles in which that force is born. We also expect to see the gravitational waves that are produced in the birth of the universe, at the very beginning of the universe, using this technique of that I referred to as CMB polarization. Something that is thought perhaps to have been what we call vacuum fluctuations came off of the Big Bang. And in the early moments of the universe, the first 10 to the minus 33 seconds of the universe, those waves, whatever they were, are predicted to have been enormously amplified by the phenomenon of inflation. And then those strong waves are predicted to have interacted with a hot gas in our universe when our universe was 380,000 years old. And that gas was producing what is now called the CMB, or cosmic microwave background. These gravitational waves are predicted to put a pattern of polarization on this CMB. And that is the holy grail for electromagnetic cosmology these days, to see that polarization signal and from it then infer details of the gravitational waves that came from the birth of the universe. And I expect that this will be done successfully with the various noise sources that they are fighting with taken care of and under control within the next decade. And what they will see will be a spectrum of this polarization that is a combination of the influence of inflation and the birth of the universe itself. I want then to wind up with just a few minutes of discussion of wormholes and time travel. Just because if I'm talking about the warp side of the universe, I don't know how I can resist saying a little bit about this. The concept of a wormhole was devised by Hermann Weyl, a great mathematician, in 1928. It was then explored in more detail by Albert Einstein and Nathan Rosen in 1935. And here is an image of what a wormhole could look like, taken from the backstory for the movie Interstellar. You have our solar system up here. This is near Saturn. You have a very dense and bright galaxy there. This is our universe. It's bent around in the higher dimension in the bulk. So the distance across the bulk between our solar system and this very, very distant galaxy might only be a few kilometers. And if there's a wormhole that stretches across, a bridge that stretches across, then if you then are Eugenie von Tunzelmann, a slew of great artists at your disposal, you make a painting of the gaseous nebulae in this galaxy. If you're me, you write down the equations to propagate that light from that galaxy through the wormhole to a camera. And if you're Oliver James, the chief scientist of the double negative team, you program the computer to solve the equations, and you build an image of the wormhole near Saturn. The wormhole is much closer to you than Saturn is, and this is light coming through that wormhole as computed by solving Einstein's equations by the members of the team that produced the visual effects for the movie Interstellar and got the Academy Award and the British analog, the BAFTA, for their visual effects work. So, and here is a real trip through the wormhole. This is not the trip that you saw in the movie Interstellar, because the trip that you saw in the movie Interstellar was too boring, and this was the one place in which Christopher Nolan, who was the director, said, okay, and I agreed, we will depart from the truth. So this is a true trip through the wormhole, but it's the wormhole in the movie Interstellar. So the bending of light around this wormhole makes two images of Saturn, one on one side, one on the other side. You're now entering the wormhole, you're passing through the wormhole, you're now on the other side, and the trip is finished. And that was not very interesting. Well, maybe it was interesting, it was not very exciting, and doesn't make for a good movie, but that's what it would really look like. Let's just do that just one more time. Okay, so two images of Saturn, one on each side. You're entering the wormhole mouth now. Those are nebulae on the other side of the wormhole. You're through the wormhole. You're on the other side. So that's what a trip through a wormhole would really look like. There's a problem with wormholes, however. Martin Kruskal and John Wheeler in 1960 showed that if you just have a wormhole and you don't do anything special to hold it open, then it will self-destruct. It will pinch off. So here is a wormhole. And there is a photon, a particle of light, traveling as fast as possible at the speed of light down into the wormhole and trying to travel through. But as time passes, the wormhole pinches off. The photon is caught here in the middle, and you're left with two singularities, one on the upper sheet and one on the lower sheet, and the photon and nothing else can get through. Is it possible to hold a wormhole open? Conceivably, but you have to fill it with something that anti-gravitates, that repels the two walls against each other. This is called exotic matter, is one way to phrase it. It has to have negative mass so it will repel gravitationally. And for physicists in the room, exotic matter exists. It's been built in the laboratory. It's associated with the Casimir vacuum and the squeezed vacuum. So we know how to build exotic matter, but tiny, tiny amounts. And there's strong reason to believe that you can't get enough exotic matter together ever, even if you're a very advanced civilization, to hold a wormhole open. So wormholes in our universe, can they occur naturally? Almost certainly no. Can they be made by an advanced civilization? Possibly. As Wheeler first speculated, and this may well be true, on tiny length scales, 10 to the minus 33 centimeters, the length scale on which Einstein's relativity fails, and these new laws of quantum gravity take over, there may well be a froth of wormholes, just a huge mess of wormholes, like soap suds in like a mess of soap suds that are there, fluctuating in and out of existence in a so-called quantum mechanical way. You can imagine a very advanced civilization grabbing one of these fluctuating wormholes, enlarging it to big size. You can imagine it. I don't know how you do it, but you could imagine it. If this were done, could this advanced civilization hold the wormhole open? Probably not. It requires, we think, too large amounts of exotic matter, so much that the laws of physics will prevent it. But when speculating beyond the frontiers of firm knowledge, as I'm doing here, it's informed speculation, but it is beyond the frontiers of firm knowledge. I've been proved wrong many times, and sometimes quite spectacularly. So don't take my pronouncements that wormholes are impossible too seriously. And finally, I'm going to send my wife on a trip out into space to make a machine for traveling backward in time. So I take a wormhole with two mouths. I hold one mouth down here at home. Carol Lee takes the other mouth in her spacecraft. And she goes out at nearly the speed of light out into the universe, turns around, and comes back to Earth. Now, and this is based on an analysis, a technical paper that I published in 1998 with two students, Mike Morris and Ulva Yurtsever, and that amazingly we did get published in a rather prestigious journal called Physical Review Letters. And it basically generated the efforts to understand whether time travel is possible or not in this modern era. So, looking through space, well, let me back up. There's something called the twins paradox, where if she goes out at high speed and then comes back to Earth, she ages very little and I age a lot. And so that, looking out through the universe, that's what she sees. When she's back here on Earth and we are side by side, she with her wormhole mouth, I with mine, I'm a very old man. She just sees me, and I'm a very old man, she's still very young. She likes when she makes the trip and I don't make the trip. But however, as seen through the wormhole, if we're just holding hands and our wristwatches are there, they tick at the same rate down inside the wormhole. You can show that this is true. And so as seen through the wormhole, if she's young, she sees me through the wormhole as young. And so it's a peculiar thing now. I, as an old man here, can go out and over. She's arrived back, and I go into her wormhole mouth. I see myself through the wormhole mouth as a very young man. I go into the wormhole mouth, I go back and meet myself. And I've traveled backward in time. And this was basically our technical paper, which said that this is what happens and proved that that was what happened. And wormhole is now a time machine. But then in a later piece of work, together with a postdoc from Korea named Sungwon Kim, I found that the moment it is created, this time machine may self-destruct. And I can't go through the details except to say that the first thing that can travel through the wormhole going backward in time is something that travels at the speed of light. That could be light, or it could be what's called vacuum fluctuations, incipient fluctuations of light that are just fluctuating in and out of existence, that are always there and you can't block. And these vacuum fluctuations then can go through and come back and return, having traveled through the wormhole and then through space going back. They can return at the very moment when they started. Now you have twice as much of these fluctuations. You go around again, return right when they started, you have 4 times as much. And pretty soon you have so much of these fluctuations that their energy may destroy the whole, the wormhole in the time machine. And we were able to show that this is a very general phenomenon that always occurs, but we were not able to prove whether or not the explosion is strong enough to always destroy the wormhole. Only the laws of quantum gravity know for sure, and we don't know these laws of quantum gravity, but Stephen Hawking has speculated that in fact the wormhole, the time machine will always be destroyed at the moment you try to activate it. He calls this his chronology protection conjecture. And I think he's very likely right based on everything we know, but again, he and I could both be wrong. Well, let me just finally wind up by saying that when I was a student, there were a lot of speculations about warp side of the universe. Today, roughly 60 years later, we've observed black holes and gravitational waves and the Big Bang, all objects and phenomena on the warp side of the universe. We doubt that wormholes exist. We doubt you can have backward time travel, but we don't know for sure. And in the coming years and decades and centuries, we expect that gravitational waves will reveal a great deal about the warp side of the universe, will likely revolutionize our understanding, actually not just of the warp side of the universe, but of the bright side of the universe as well. Gravitational wave observations hand in hand with electromagnetic observations. Thank you.
Thank you very much, Kip, for this marvelous concerto. I think it was the best concerto this hall has experienced. The problem is that after concertos, you don't ask questions. We preliminarily agreed that discussion will last till 6:20, which is exactly
well, let's
now.
give them 10 minutes.
No, sure.
We'll give them 10 minutes, but then we have to, Carolee and I have to disappear in 10 minutes.
That's right. They have actually Black Theater performance at 8 o'clock about when technology is called déjà vu. when technology will be too much advanced, it's a quotation by Einstein, so then human relations will completely cease to exist, and then we all will be just idiots. But they are looking forward to this. So in any case, so this will be at 8 o'clock and they should still eat something. So please, nice questions. Okay.
There should actually be, thank you, there should be a gravitational noise throughout time-space. Am I right?
Gravitational noise. Yes.
Are there any resonances, anything like that?
Yeah, so there should be a gravitational noise, or what we call technically a stochastic background. And the statistical properties of this noise will be very important to tell us about processes in the universe. And one part of that noise may be these stochastic waves from colliding bubbles of the newly born electric and magnetic force. Another part of this noise will be the amplified waves from the birth of the universe. And so what we expect is that within the next several decades, we will be seeing this gravitational noise, and we will be analyzing it statistically to try to pull apart the various sources. But the most interesting of those sources will be things that happen in the first small fraction of a second of the life of the universe.
I'd like to ask you if we can apply the Fermat's principle on lenses made by the black holes, because if the ray goes to the black hole, it will make a longer distance.
Yeah, so yes, you can. So Fermat's principle is a particular way to understand the propagation of waves when the wavelength of the waves is small compared to the size of the black hole, for example. And you can apply Fermat's principle to study this. And you do find then that if the gravitational waves from some source, just like light, go down and they go around the black hole, and then on, they travel a greater distance and there is a time delay. And the gravitational waves experience this in just the same way as light does. Yes.
So, are gravitational waves polarized? Or if yes, is it possible to detect this and other phenomena that are result directly from this?
Yes, so you know about polarization of electromagnetic waves. If you have Polaroid lenses, then you can block out the bright light that is shining off of the surface of the ocean, for example, because that light is polarized. And so this technique of, this issue of polarization, which has to do with electromagnetic waves, with the direction that the electric field is oscillating, whether it's like this or whether it's oscillating like that, it's a very powerful tool for technology and a tool that is used in helping people to see. Gravitational waves are similarly polarized. In the case of gravitational waves, you can stretch and squeeze along these directions. That's one polarization. Or you can stretch and squeeze along those directions. That's the other polarization. And there is a gravitational waveform, a pattern of stretching and squeezing that may be different for this polarization than for that polarization. So there's an international network of gravitational wave detectors that is being assembled, and it will be used to measure both polarizations of gravitational waves, and thereby get twice as much information out as we now do when we see only one polarization. She's asking a question. Oh.
Can you tell us something about the research of the food rays of
the footprints. Oh, the memory, okay. So gravitational waves from some sources have memories in the sense that you have a stretching and squeezing, but after the wave has passed, your detector is left stretched. It doesn't return to its original separation. It may be left stretched along this axis and squeezed along that axis. And that's called the memory because it remains after the entire wave has passed. And it carries very interesting information. Among other things, it tells you basically how much energy was carried by the gravitational wave, not toward us, but in other directions, because this memory is produced by the gravitational pull of the energy in the gravitational waves that went in other directions. It's a very peculiar thing. And so these memories are weak enough that it has not yet been seen, but there are efforts underway to see it in statistical ways by combining the data from many black hole collisions in such a way as to pull out the memory effect by building it up by combining data from many black hole collisions. With LISA, where we will have much stronger signals, we may see this memory of the gravitational waves that are produced just by one pair of black holes colliding. This is of high importance for fundamental physics because these memories are closely related in some way, some deep way, to the phenomena of information lost down black holes. There's a mathematical and deep physical connection. So it's of interest for that reason, but it's also of interest because it gives you additional information about the source. But those efforts are underway. I think it will be a few years before even statistically combining lots of black hole data, we will see the memory. But with 3 black hole collisions in the last 5 days, we're on our way toward getting a lot of data that could be used for something like this.
This memory effect, that was correct question, is still the subject of theoretical investigations, so there are papers in physics, etc. I should not forget to say one thing before we close, namely Kip was so kind that he started by doing Hyde Park Civilization on Wednesday morning. Of course, there was no projection of Hyde Park Civilization, and they, as I understood, are now finishing at the end of May. So most likely Hyde Park with Professor Thorne will be in September. And after he returned from the television, so the most diligent lady there who prepares all material for Daniel Stach, whom you know, of course, from the screens, but the lady is Gabriela Cihlářová. She phoned me and said that they probably didn't have such splendid Hyde Park as with Professor Thorne. So we could look forward for that. So last question. Okay, so there was somebody quite quick over there, yes? Tamhle u toho okna, já nevidím tam.
You said yesterday that gravitational waves exhibit similarity to electromagnetic waves. Might you also expect some oddities of wave-particle duality, like things downstream of the double-slit experiment and such?
Yeah, so wave-particle duality, of course, is a very interesting and very important phenomenon that with electromagnetic waves, if you have a lot of photons, particles of light, that are all doing the same thing at the same time, side by side, then they behave like a wave. And you can't see the fact that you have discrete particles unless you have very, very high accuracy. If you have only a few particles doing the same thing, you can then see the discreteness of the particles, or if they're all doing something different. And so this fact that light can behave like a wave or like a particle is a very deep fact of high importance, also high importance for technology. Gravitational waves should exhibit this same phenomenon. But in the case of gravitational waves, we today have a good enough sensitivity to see waves where you have typically something like close to 10 to the 40. So that's something like a billion, or something like that. Gravitons all doing the same thing side by side. Or to put it differently, you have a mean occupation number of the quantum states of the graviton field that is something like 10 to the 40 for the waves that we see. And for that portion of the gravitational wave field that is detected by our detectors. There's no hope whatsoever, I think, in the next several centuries to get sensitivities that are good enough to see the discrete gravitons and see the particle side of the wave-particle duality. Now, again, I sometimes prove to be quite wrong, but at the present time, I don't see how one would do this because it requires technology far, far beyond what we have achieved in these past 50 years. So I hope that someday this will happen, but I don't see how.
Yesterday evening, Kip said that the nicest cities are San Francisco and Prague. He even wrote it into this book. You can see it in afterwards of this Czech translation of his black holes. So all those who have prepared questions, please don't forget them next time.
And thank you. I have to say this is the end of a wonderful week I've had in Prague. I also had wonderful weeks twice before in 66 and 67, then a long gap. And I assure you, I will not have anywhere near that long a gap before my next visit. Thank you very much.